Let's get back to the cases that we have yet to cover. So I have to give you 3 pieces of information. That's how this game is played. And we saw that if I gave you 3 sides, then you use the law of cosine. You don't really have a choice. That's the only one that's available in the toolbox that will work. If you have 2 sides and the included angle, that is also a case for cosines. You got that full set of information. A, B, gamma, A, beta, C, or alpha, B, and C. So we use the law of cosines. The law of sines is not really a choice. The third example that we did, the example we did today, is 1 side and 2 angles. So if you've got 1 side and 2 angles, you're subtraction away from 1 side and 3 angles and abundance of information. So just subtract and then use the law of sines. The only other case, the only other way I can give you 3 pieces of information is to tell you 3 angles. But 3 angles is not enough to determine 1 triangle. This is an infinite number of similar triangles. We could use some information to find out the ratios of these sides, but that's not generally something that we're going to ask for. If we have 3 angles, we're not looking for 1 triangle. We're looking for a whole category of similar triangles. That's not really one that we're going to worry about. So we have talked about the law of cosines for 3 sides, the law of cosines for 2 sides in the included angle, and 1 side plus 2 angles. That's a law of sines, subtraction, then the law of sines. So the last one left is 2 sides and an angle that's not included. So this means that we're going to have to use the law of sines. But something weird happens in this case, which is why I saved it for last. If you're given 2 sides and a non-included angle, there's a possibility that you make no triangle at all, that the information will not give you a triangle. There's a possibility that we get 1 triangle. There's also the possibility that we get 2 triangles. And there's a 4th possibility that we get 1 triangle. So it's 0, 1, 2, or 1. The way we get 1 triangle is different. That's why I listed it twice. That first one that I listed is pretty hard to land on. So let's take a look at 2 sides and a non-included angle. So this is going to be a set of information, A and alpha, B and beta, C and gamma, plus 1 other side. So we'll have opposite information plus 1 side. So let's suppose that side A is 15. Angle alpha is 37 degrees. Right away, if I'm only going to give you 3 pieces of information, we know that this is not going to be a law of cosines question. We've got A and alpha, we've got opposing information. If I want to make then I need to give you, so if I want you to use the law of cosines, sorry, if I want to create the ambiguous case of the law of sines, then I'm going to give you another side. Let's say B is equal to, we'll fill this out in a minute. What I want to start with is naming the parts. We're going to have 2 sides and the angle not included. This 37 degrees, we're going to call this the given angle because it's the given angle. We're not really clever with our naming of things anymore. We used to come up with weird ass names for things. Like if you look at coordinates, X coordinate and Y coordinate, that's what we call them today. X coordinate and Y coordinate for the horizontal and vertical components. But one of those is the abscissa and the other one is the ordinate. There's actually words for those two things. Here's how important that is. I don't know which one is which. I've been doing this for like more than 20 years. I've known at one point, I don't think it's really that critical to name the pieces. You know what I mean? Back in the day, we didn't have like television and Xboxes and stuff, so we came up with names for shit. I think that's my explanation for why it's that way. Also, like when you add stuff, we just call them terms. That way, if you're subtracting, it's terms. A plus B, A and B are terms. A minus B, A and B are terms, right? But when you're adding A plus B, A and B are called addends. But when you're subtracting, it matters which one goes first, because A minus B is the opposite of B minus A. One of the terms in a subtraction is the minuend, the other one is the subtrahend. The result is the difference. We know that word. I don't know which one is the minuend and which one is the subtrahend. Been teaching math well over 20 years. I think I knew at one point, but I can never remember. It's one of those things you look up and then immediately forget. You know what I'm talking about? Because in the modern era, you never have to spend much time not knowing a thing. You're just like, oh, I'll just look it up. You grab your phone. You can just ask your phone in words for the thing. What are we talking about? Oh, yes. So we're going to name some parts. Alpha is going to be called the given angle. A is the side opposite the given angle. So I'm going to call it the side opposite the given angle. Maybe we should get someone more creative up here to name the shit, but you got me. So A is the side opposite the given angle. And B or C, whichever one I happen to give you, that's just going to be called the other given side. So the parts in play are the given angle, the side opposite the given angle, and the other given side. My proposal is that depending on the value of B, depending on the value of the other given side, we can produce 0, 1, 2, or 1 triangles. So the ambiguous parts different values of the other given side can produce 0, 1, 2, or 1 triangle. So how can this be? I'm going to say this, the other given side is going to be, I had to decide which of the four I wanted to open with. And I'm going to open with this one. I'm going to say the other given side is, actually just go this way. Oops. Different values of the other given side and the side opposite the given angle can be 0, 1, or 2, or 1, 5. All right. So what we want to notice is that we have two sides and the angle opposite one of those sides. That's when we know that we are in the ambiguous case, and there could be 0, 1, 2, or 1 triangles. We just have to know that we're in the ambiguous case. Let's talk about why this is going to produce these four possibilities. Let's suppose that we have an angle. So the given information is, let's say this is the given angle. The other piece that we're going to have is the side opposite the given angle. The side opposite the given angle has to connect this end down to this line down here. The side opposite the given angle is going to have to connect that at the end of the other given side to the line where the third side is. That's going to be this big line down here at the bottom. This is the line where third side is. And up here, we'll have the other given side. This is what has to happen. You've got to take the side opposite the given angle and connect it to the end of one end of the other given side to the line where the third side is. What we can see is that there is some minimum distance between the other given side, the end of the other given side, and the line where the third side is. So if A is too short, if the side opposite the given angle if the side opposite the given angle is too short, then we have no triangles. If you find that the side opposite the given angle is too short, then the ruling on the field is no triangles. So the referee will make a triangle and then shake his head no. That's the ruling on the field, is no triangle. I mean, they're just going to tell us what it is anyway, because they got microphones now, but they still have to do the dance. I'm wondering if a ref ever forgot what the signal is. It's like, oh, like forgot what the how to do pass interference, and so he's like, oh, pass interference on that guy. Like, just like say what it is. Is it? I think this is pass interference, right? So instead of being like, oh, pass interference, doing the interpretive dance along with the lyrics, he just says pass interference and leaves his hands quiet. I don't know if you're even allowed to do that. I'm waiting for a ref to be like, oh, no, I'm not using my hand. Then wherever his boss is sitting, who's been giving him guff about not using the hand signals, he just starts kicking his boss off. That's pass interference on number 15. Oh, check it out. That's a touchdown. You know what I mean? I know I should take the job of football referee more seriously, but maybe this is why I don't get to do it. Also, I don't know all the rules of football because all the rules of football don't really make sense. It's like a hodgepodge of just like patching stuff. Baseball, all the rules make sense. It's like a consistent set of rules. Even though it sounds weird when you read them, makes perfect sense in application. Football, if you have to slow down things to super slow-mo and 4K to figure out what the ruling was, as far as I'm concerned, the ref on the field got it right. If you have to do that, if you have to go into bullet time in real life and watch as everything slows down, like it's the movie 300, the movie 300, if you just play it at a normal speed, is like 20 minutes long. But there's so many slow-mo sections, just like, they expect referees, which are human beings, to be able to watch things in slow motion in real time, so they get the call, quote, right. Who cares? If it's not that obvious, if you have to look at it in super slow-mo from a bunch of different angles, the ref was right. And any head coach that starts crying about it is immediately ejected, not from the game, from the profession. And the explanation is just going to be, we don't need any babies around here. Get out. It's a game. You know what I mean? Every time I see like a head coach throw the challenge flag on the field, all I hear is, no, you got it wrong. You baby. Yeah. What are we talking about? Oh yeah, no triangles. That's the referee's thing. It doesn't come up very often because there's not a lot of trigonometry. Like you've heard of trick plays in football. But have you heard of trig plays in football? Quarterback's error. All right, law of cosines on 3. And the teams are going, what? And like the linemen, they're like, once they hear law of cosines, they all pull out calculators. And then the defensive line is like, oh, what the fuck is going on? And they start making calculations. All right, maybe this is why I'm not allowed to do football. So one thing that could happen is that the side opposite the given angle is too short to reach, to connect the end of the other given side to the line where the third side is. Another thing that could happen. What did I make it? Wow, 3. Excessive. Number 2 thing that can happen. It could be that the side opposite the given angle exactly makes that distance. It's exactly the distance from the end of the other given side to the line where the third side is. In this case, we get one right triangle. where the side opposite the given angle fits perfectly. And we'll get one right triangle. This is known as the Goldilocks case. Not really, I'm just trying to make that a thing. I get like 20 students in trigonometry to walk forward saying, oh, it's the Goldilocks case every time this happens, and it will become a thing. Just have to make it into a textbook, not written by me. Once that happens, I'll get the last achievement, unlock the last achievement in the teacher profession, and I can go do something else. It's gonna take a while to get this 100% unlocked. Especially since one of the achievements is like grade shit on time, and I still don't have that one after 20 years. But this is the Goldilocks case. So that could happen. The side opposite the given angle fits perfect. It matches exactly the distance from the end of the other given side to the line where the third side is. Another thing that can happen is that the side opposite the given angle is a little bit more than that distance, but not too much. So but here, if this is the shortest distance from the end of the other given side to the line where the third side is, if I make the side opposite the given angle a little bit more than that, then I can make it go to the left and to the right and build two triangles. I can have the side opposite given angle go this way. Or if we just swing this same distance around like on a compass. We get two possible angles. Imagine that side being just long enough. It's like if I swing it to one side, I make this one obtuse triangle. And if I just swing it back the other way, that line will hit up the line where the third side is again. And so if the side opposite the given angle is a little bit more than a perfect fit, then we'll have two possible triangles. So if the side opposite the given angle is a little bit more than a perfect fit, but not so long, then we'll end up with two triangles. Imagine that green line just dangling, and I could make it line up two different ways. Then the fourth thing that can happen is back to one triangle again. So imagine the height down here. Imagine how we get two triangles. We get two triangles by where the side opposite the given angle is a little bit more than a perfect fit, and so we could swing it both directions and come up with 2. If I make it too long, if the side opposite the given angle is too long, then it won't meet the line where the third side is. It'll swing right past the vertex of the given angle and all the way around, and it just keeps on spinning and spinning and spinning. I'm just kidding, it doesn't keep on spinning. It stops when it gets to where the other one is going to be. That happens when the side opposite the given angle is greater than the other given side. So here's the other given side. If I make another side the same length, if the side opposite the given angle is greater than the other given side, I'm only going to be able to make a triangle going this other direction. So if the side opposite the given angle is greater than the other given side, then we'll be back to one triangle. If the side opposite the given angle, I can't swing it to either side of the height. Because the side opposite the given angle, if I tried to swing it to the other side, it would go past the vertex of the given angle. So the ruling is going to be one triangle. I just want you to imagine we build the angle where one of the segments on the angle is the other given side, and we're trying to make the side opposite the given angle reach the line where the third side is. It could be too short, no triangles. It could be just perfect, one triangle. A little bit more than perfect, but less than the other given side, we get 2 triangles. Greater than the other given side, back to one triangle. Notice no matter if the side opposite the given angle is greater than the other given side, we have one triangle, and this can go on forever. We can make the side opposite the given angle as long as we want. We just have this very long, very sharp triangle. That's why we don't want to go too far, because then the problems get too sharp and I start cutting myself. So I don't want to get cut on all these sharp triangles, so I try to keep them a little bit dull. It's a math class. You don't have to work hard at keeping things dull. Any questions? Everybody okay? All right. So we need to be aware when we're in the ambiguous case so that we know how to deal with it. This seems like a lot to think about. The good news is we don't have to remember all the things that we don't have to remember which. We don't have to know which of these cases we're in. You don't have to know what's going to happen. The numbers will tell us what's going to happen. We just have to do the right things. We have to read what the numbers are telling us. We start making our calculations with the law of signs, and that will let us know what's going to happen. 0, 1, 2, or 1. So we'll talk about the ambiguous case of the law of signs on Thursday. That's going to do it for today. I'll see you all on Thursday. Everybody have a good couple of days, and thanks for playing.